the first thing I'm going to do is talk about composition, percent composition and part per million composition. And so this is related to the problem, but not exactly the same as the problem. But let's if we have 17% chlorine solution, or not 17, 7% chlorine solution, there are different ways of expressing that. So to convert it from a percent to a fraction, what would we do here? Yeah, but it doesn't have to be grams. It could be anything. And so if we divide it by 100%, then we get 7 out of 100. And this could be grams, it could be pounds, it could be ounces. Whatever units you want, it's going to be the same ratio. And so chemists use grams, and so we're just going to go ahead and use grams. And so this is going to be 7 grams of what per 100 grams of what. We wouldn't leave it like this because this is in Chem 1A. We have to be very careful what the units are. 7 grams is not equivalent to 100 grams. It's going to be 7 grams of what in 100 grams of what? 7 grams of pure chlorine in a 100-gram mixture. And the 100-gram mixture is going to be the chlorinating solution. So we're going to call the pure chlorine just Cl, and the chlorinating solution ClSOLN. Now chlorine is a diatomic element. Normally we call it Cl2. But these chlorinating solutions often aren't elemental chlorine. You know, a lot of these chlorinating solutions will have bleach in it, which contains chlorine, but other atoms as well. So I'm just going to call it Cl rather than Cl2. And so this is going to be 7 grams of pure chlorine in 100 grams of chlorinating solution. And so we can convert it from percent to fraction. And the fraction, this is a conversion factor. This is what we call an intensive property or an extensive property of this chlorinating solution. Intensive or extensive? Of the chlorinating solution. Intensive. It doesn't matter if you have a gallon or a million grams, it's going to be in this ratio. So for example, if I had 1,000 grams of chlorinating solution, it doesn't matter, I'm going to have the same ratio. Rather, it's going to be 70 grams of chlorine per 1,000 grams of chlorinating solution. So it's always going to occur in the same ratio. That's an intensive property. And so I could flip this over. So if I have 100 grams of chlorinating solution, it's going to be 7 grams of pure chlorine in that. And these are what we call conversion factors. Conversion factors are intensive properties here, usually intensive relationships like this. We could also convert this into decimal form. You know, in decimal form, we just do the division here, and it's going to be 0.07. And really, decimal form is 0.07 over 1. 0.07 grams of chlorine per 1 gram of chlorinating solution, which is just 0.07. You can put the units in there. All right, now we do the exact same thing. If we have 1 ppm of chlorine in pool water, then a part per million and a part per 100 are pretty much the same thing. Here we just divide by a million to get it in fractional form. So if I divide it by a million, and it doesn't matter the units here as well. This is ppm by mass. Typically, these are composition by mass. Composition by mass. And so what I'm going to end up is 1 out of a million. And it doesn't matter the units again. It could be 1 pound of what per million of what. And so it's going to be 1 pound of chlorine, pure chlorine, in a million pounds of pool water. Okay, and so the unit here, since we're chemists, we use mainly grams, so I'm going to use grams too. So it's going to be 1 gram of pure chlorine in a million grams of pool water. And that would be it. So we can go from the fractional form or whatever to whatever. So for example, I know that there are 7 grams of chlorine per 100 grams of chlorinating solution, what would this be in ppm? And so all I do to convert it to ppm is I just multiply it by 1,000,000. And so if I have 7 out of 100, the grams will cancel. And I want to convert that into ppm. I'll just multiply. Well, I'll just leave the grams in there. I'll just multiply by 1,000,000. If I want to convert it into a percent, what would I multiply it by? I'd multiply by 100. And so if I convert it, let's say I'll have 2 paths here. One path I multiply by 100%, and I end up with 7%. Another path I end up multiplying it by 1,000,000. And what would this be? Well, that would be 10 squared. That would be 10 to the 6th. That would be 10 to the 4th. This would be 70,000 ppm. And so the chlorinating solution, we could express either in percent. It would be 7% chlorine in the chlorinating solution. Or we could express it in terms of ppm. It would be 70,000 parts per million chlorine in the exact same solution. For parts per billion, we could do that. But what would the concentration be, or the composition be, in parts per billion? So we just multiply it by 1 billion ppb for parts per billion, and I would get 70 million parts per billion chlorine. Well, this is kind of a hassle. 70,000 ppm, 70 million parts per billion. That's too big. It's much more convenient to express it in terms of percentage. But some things are too small to express in percentage. So the things that are too small to express in terms of percentage would be something like this. Let me go back up here, and this to save time. I'm going to express this in terms of percent. So if I have 1 ppm chlorine, what would that be in percent? So in percent, I'll just take the fractional form and multiply it by 100%, and then see what I get. If I take the fractional form and multiply by 100%, that's going to be 10 squared divided by 10 to the 6 is going to be 10 to the minus 4. And so 10 to the minus 4 will be 0.0001% chlorine. And so that's kind of small. And so it's a little bit of a hassle. So it would be easier to express the concentration of the chlorine in the pool in ppm, because if we expressed it in terms of percentage, it would be 0.001%. Versus the concentration of chlorine in the chlorinating solution would be much easier to express in terms of percentage, because the others would be too big. And so what we do is we pick and choose which one we want to express it in, depending on how convenient it is to write the final answer. Does that make sense? But essentially they're all the same. Do you see that they're all the same? Pretty much? Okay. Now, when we use these as conversion factors, we use the fractional form. So what we do, when I get a problem like this, the first thing I do is I just extract all the information that's given. You know, I want to know what's given, all the conversion factors that are given. The conversion factors are typically these intensive relationships, like this one here. And so I have 7% chlorine by mass. I'm going to go ahead and just write that here. And so that is going to be 7 grams of chlorine pure over 100 grams of chlorine solution. Chlorine solution is a mixture. It's a homogeneous mixture. And so in this 100 grams of mixture, there's 7 grams of chlorine and 93 grams of other stuff, like water, etc. When we do these as conversion factors, we can invert them. And so this one is great at converting grams of chlorine solution to grams of pure chlorine, and this one would be good at converting grams of pure chlorine to grams of chlorinating solution. And so we just do or, depending on what we want to do. And so we'll just string this on as a conversion factor. This would be one step in climbing Mount Everest. And so we can figure out this. A one-step conversion is usually pretty easy. So for example, if I had 2 million grams, no, I shouldn't do that. I had 200 grams. If I have 200 grams of chlorinating solution, how many grams of pure chlorine am I going to have? 14. And if I have 21 grams of pure chlorine, how many grams of chlorinating solution would contain that? 300. And so one step in climbing Mount Everest is pretty easy. It's just when you look at the whole thing, it's overwhelming, right? But one step should be easy. Okay, what's the other step? Well, the ppm chlorine. So they give you a hint here. And so they tell you, think of ppm as 1 gram of pure chlorine per million grams of pool water. So if I had 2 million grams of pool water, how many grams of chlorine am I going to need? If I had 2 million grams of pool water, I'd need 2 grams. 3 million grams would require 3. And so that's intensive. It doesn't matter how many grams of pool water I have. I'm going to have this ratio that I can always figure out. It's always going to be the same ratio. That's an intensive property. Or we could flip this over and think in terms of grams of chlorine. So let's say I had 5 grams of chlorine. Well, if I have 5 grams of chlorine, then that's enough for how many grams of pool water? 5 million. And so, but I'm going to keep this as 1. 1 over a million. I mean, 1 million over 5. Or not 5, but 1. Let me erase that. Oops, I was doing it in blue. So I think everybody can make it up one step up Mount Everest, right? But doing the whole thing might be more challenging. But if we can make it up one step, then we can make it up another. It's just stringing them all together that's the hard part. But for us, it's stringing them all together is just a matter of endurance here. You know, how much perseverance do you have to keep trying different steps? You know, if one step fails, do you have enough perseverance to succeed or not? All right, then we have densities. Now densities are a bit different because we should know, for example, the density of the chlorine solution. What's the density of water about? 1. And so the chlorine solution has a density of 1.10. What does that mean, 1.10 grams per milliliter? It's 1.10 grams of what? This is going to be chlorine solution over a milliliter of chlorine solution. It's like the density of gold. The density of gold is 20 grams per milliliter. 20 grams of gold per milliliter of gold. And so it's the same thing. And so this is a little more dense. As you'd expect, I mean, if you dump a whole bunch of chlorine in water, 7% chlorine, the weight of it's going to go up because chlorine atoms are heavy. And so this is heavier. So this is going to relate chlorine, milliliters of chlorine. So let's say I had 1,000 milliliters of chlorine solution. How much would that weigh? Or if I had 1,000 grams of chlorine solution, what is the volume? And so that's 1 milliliter of chlorine solution per 1.10 grams chlorine solution. And so again, another step. So if we take these steps individually, that's 3 steps. You know, how many steps are we going to have? It's not going to be an infinite number of steps. And it's a puzzle. It's a puzzle just stringing together these 3 steps so far. But maybe there's a gap. You know, if there's a gap, then we're missing a puzzle piece. Hopefully we're not missing any puzzle pieces. They should give us all the puzzle pieces, so there should be no gap. Okay, the next one is this density. They give us a density of 1.00 grams per milliliter for the swimming pool water. And what that is 1.00 grams of pool water per milliliter of pool water. And so what is the density of water? Qualitatively, what's the density of water? It's 1. Qualitatively, the density of water is 1. And so you might go, hey, this is like pure water. But the pure water is not pure. I mean, would you drink pool water? I've drank it and fortunately haven't died because maybe they kept it at 1 ppm. But if they kept it at 7% or 70,000 ppm, I probably would have died, you know. But fortunately I didn't die, but it seems, how can that be? Because isn't that the density of pure water? Pure water has a density of 1. This pool water has a density of 1. So isn't it pure water? And the answer is no, it's not, because 1 is very qualitative, right? Actually, the density of water is 1 at 4 degrees Celsius, but when you get to room temperature, the density of water is like 0.99, 0.98. And so this is actually heavier than the density of water. So if we were being very quantitative, And we determine the density of water. There are 3 ways or 4 ways to determine the density of water. One is to go ahead and measure it by experiment, but fortunately somebody's already done that. So number 2 would go to the data table. You go to the data table, look at what is the temperature of the water, and then you go in the data table and look at the temperature and the density and read the density off the data table. That's 2, or 1. What's another method of determining the density of water? Another method of determining the density of water is by graphing it. You remember the curve? It's kind of a funny curve. You graph it and then go to the temperature and then read the density off the graph. That's called graphical analysis. And finally, what's the other method of determining the density of water? We could use the raw data, the observations. We could use the data table, which would be part data reduction, or we could use the law of the density of water. What was the law of density of water? Called? The law of the density of water was called the empirical equation describing the curve. Remember that? And if that empirical equation describing the curve was pretty good, that is, had a good R² fit to it, then we could be pretty confident in the law. Because we have things called law and rules. And if you think about it, are they the same, law and rules? How would you define the scientific rules versus a scientific law, or law of nature? You know? Law should have a really good fit to what's observed. You know, the R² should be very close to 1. But rules are a lot looser. There are a lot of violations for rules. You remember the solubility rules, nomenclature rules, all these things? There are lots of exceptions. And so rules aren't as strict as laws. And so I didn't put rules into my scientific method, but the rules come about when you see certain patterns. And these patterns are good, but not good enough to call a law. You know, that kind of thing. Well, anyway, so this is a little more dense, because if we're at room temperature, then the density of water, you know, if we're being more quantitative, more sig figs, then it's going to be lower than that. And so this is a little more dense than pure water. Not only that, we can't be this precise for pure water, because the density of pure water changes about 4% over the temperature range. But anyway, this is another step. And so we could say 1 milliliter of pool water, PW, is equivalent to 1.00 grams of pool water. And so one of the big differences is we're always working with composite units in Chem 1A. A composite unit is, there are 2 units that we got to deal with. One is grams, the other is chlorine solution. You know, grams, pure chlorine, 2 units. And what we do with those 2 units is either we cancel both of them out or one of them out. It's like acre feet. We try to cancel out both of them, but sometimes we can't. We just got to cancel out one of them, acre, leave the other one, and or cancel out feet later in a subsequent step. But we aren't going to cancel out necessarily both together. And so that's often what happens with some of these. And so these are all intensive properties. Normally when we start a conversion factor problem, we start with an extensive property. And so the other item that's given here is it's an 18,000 gallon swimming pool. 18,000 gallon, is that intensive or is that extensive? That's extensive. 18,000 depends on the amount. So if you have 20,000 gallons, is this the same as 18,000 gallons? No, it's 20,000 gallons. So it's different. It's more or less. You could have 17,000. And so normally we'll start, if now that is, most of the problems you do, you start off with the extensive. Sometimes you'll start off with the intensive. So for example, miles per hour. Miles per hour is intensive, but you might want kilometers per hour. If you want kilometers per hour, that's also intensive. So you might do a unit conversion problem there. But what we're going to do here is we're going to start off with the intensive property, which is going to be 18,000 gallons of pool water. All right, now this is the strategy that I do. I mean, I just try to take one step at a time. And so taking one step at a time, I'm going to try to cancel out gallons or I'm going to try to cancel out gallons of pool water. But we just went through all the units up here, and there was no gallons of pool water. And so we aren't going to be able to cancel out both of them. So I'm either going to cancel out one of them, gallons, or the other one, pool water. There aren't any other options, actually. And so I'm just going to cancel out gallons. And I'm going to go from gallons to what? Liters. So this one you don't have to have memorized. This one would be a given, 3.785 liters. Because this one's good to how many sig figs? 4. This one's not exact, though. And so this is just good to 4. You would know qualitatively it's about 4 liters to a gallon. But, you know, if we use the qualitative value, that's kind of going to lead to a more significant error. And so we aren't going to round this to 4. It's like, I have some solution. It's about 1 gram per milliliter. Would you trust that it's pure water? No, you want to be more quantitative than that. You know, 1 gram per milliliter, yeah, it could be pure, but we don't necessarily know. And so we just do one step at a time. So the gallons cancel. I don't know where I'm going. You know, this is like, I mean, there are different analogies for this. You know, this is like you're driving through a city. You kind of know the direction you need to go, and you just keep trying different streets. And if you get stuck in a dead end, you don't want to stop. You want to back up and try a different way. Or this is like if you're lost in the middle of the jungle. You know, you just take one step at a time. See where you can go. So now we're at liters, and I don't remember seeing anything with liters of pool water, so I'm just going to get rid of liters. And from liters, where can we go? Well, we can go to gallons, but if we go from liters to gallons, what's going to happen? We're going in circles, and so we don't want to be like the ants that go in circles and eventually die following the liter. But anyway, we'll go from liters to milliliters. And so now I have milliliters pool water. Do I have anything up here that has milliliters pool water? Yeah, right here, milliliters of pool water. Let's get rid of both units. So what I'm going to do is I'm going to go 1.00 grams of pool water per 1 milliliter of pool water. So now I can cancel out both units. I can cancel out milliliters and I can cancel out pool water. But even though I cancel out pool water, I'm still left with pool water. But now I'm left with grams of pool water rather than milliliters of pool water. And so now I can get rid of grams or grams of pool water. Well, I don't want to use this one here. Is there another one that has grams of pool water? Yes, there is. There's the 7 grams of pure chlorine per 100 grams of pool water. And so now I can cancel out the grams of pool water and be left with grams of pure chlorine. All right, continuing this along, I want to look for something that cancels out grams of pure chlorine. Is there something that cancels out grams of pure chlorine? Oh, actually, I made a mistake here. This is the problem with Chem 1A. The problem with Chem 1A is you can't be so sloppy like I was here, because we need to know, this is not 100 grams of pool water. What am I doing? This is the density. This is, I used the wrong one here. That's why you have to write the units. In fact, I wrote the wrong units on this. This shouldn't have been 7 grams of chlorine per 100 grams of pool water. It should have been 7 grams of chlorine per 100 grams of what? Chlorine solution. Now, if you make a mistake in the lab notebook has these permanent, what we call a permanent binding. The pages aren't meant to be torn out. And so what a lot of people would like to do is when they make a mistake, they like to tear out the page because they want to keep things clean, but that's considered very poor technique. Never tear out a page out of the lab notebook. If we make a mistake, you just write a single line or X through it, like this, so that the mistake is still legible. And then what you'll do is you'll just write the correction above it here. And so the correction is, I shouldn't have gone here, I should have gone where? So rather than using that, it was 1 million grams of pool water on the bottom, and on the top would be what? 1 gram of pure chlorine. Okay, so I just corrected it here. 1 gram of chlorine. And so now finally I get rid of the grams of pool water and I'm left with grams of pure chlorine. So now I got to get rid of grams of pure chlorine. And what will do that? Now I can use this. 7 grams of pure chlorine per 100 grams of chlorinating solution. And so the grams of chlorine cancel here. And that leaves me with grams of chlorinating solution. Now what I want to get rid of is get rid of grams or grams of chlorinating solution, but I can get rid of grams of chlorinating solution. Because what do I know about that chlorinating solution? I know that there are 1.10 grams of chlorinating solution per milliliter of chlorinating solution. And so the grams of chlorinating solution cancel, and that leaves me with milliliters. And then they want liters of chlorinating solution, so I'm just going to convert from milliliters to liters. All right, so when we check our work, the first thing is we just want to make sure the units work out. And so the units come out to liters of chlorinating solution. Well, that's what we want, liters of chlorinating solution. And then we just check the numbers here. It's going to be 18,000 times 3.785 times 1,000. Check and see if you get the same number. Times 1 divided by 1 million. Times 1, I didn't even bother punching that in. Divided by 1 million times 100. Divided by 7. Divided by 1.1. Divided by 1,000. And this is what I get. 0.8848 liters of chlorinating solution. I'm going to talk more about this particular problem, but let's first look at the sig figs. So did you guys get this when you punched in the calculator? Yeah? Okay. So that's some consensus there. But first thing is, how many sig figs do I have in 18,000 gallons? Are these zero significant, or they might be, they might not be. So if we're playing it conservative, I would say 2 sig figs. To make these zero significant, I put a decimal point there. How many sig figs here? Here? This one is not 4, infinite. This one, 3. This one, 1 gram of chlorine per million grams of pool water. That one looks like 1 sig fig, but if it's a standard, let's say the federal government or the state government or the city government requires a chlorine level of 1 part per million in their pools, then we could take that as infinite, you know. They want ideally exactly 1 ppm. Yeah, there would be a plus or minus, but here we could just call it more than 1. I would just call it infinite. Just say that's the standard. However, this one here, what would you say this? The chlorinating solution is 7%. Do you think the manufacturer got that to infinite sig figs? Is it possible to have a measurement with 0 uncertainty? No, this is not possible. So when the manufacturer made this, I would assume that they made this to how many sig figs? 7% chlorine would be made to 1 sig fig. I mean, it makes sense. Otherwise, if they made it to 2 sig figs, they wouldn't call it 7%. They'd call it 7.0%. And there's a huge difference in precision, because if something's marked as 7%, that's anywhere from 6.5 grams to 7.4 grams. And if they're unscrupulous, like some of these pharmacists, do you hear about the pharmacists that were diluting the chemotherapy medicines? Have you heard that? So they could double their profit? You didn't hear that? That's pretty bad. But, you know, if you have an unscrupulous manufacturer, maybe they're always making it 6.5, but they're not really unscrupulous, because 6.5 rounds to 7 to 1 sig fig. And so that would be legal, versus these pharmacists, that would be totally illegal. And so if they made it always to 6.5, then they'd save a 0.5 gram of chlorine for each batch, right, of 100 milliliters, which would be a huge increase in their profit margin. And so, you know, when you buy it to 1 sig fig, you don't know, but maybe they're always, maybe their precision is much better than they say, and maybe it's always 6.5. You're always getting the weakened, diluted down stuff. You know? But anyway, that's 1 sig fig. This would be how many? 3. This would be infinite. So we're only allowed 1 sig fig. The reason we're only allowed 1 sig fig here is because there's some uncertainty here. Are we getting the weak stuff, or are we getting the strong stuff? The strong stuff would be maybe 7.4, the weak stuff would be 6.5. So when we do this, we can't be so precise in our measurements. So we need to round this to how many sig figs? 1 sig fig. So this is going to be 0.9 liters. And so that means if our chlorinating solution was the strong stuff, then maybe 0.85 liters is enough, 850 milliliters. Or if it was weak, let's say it was 6.5, then we'd probably need about, 0.94 liters. Does that make sense? Okay. So one of the things is we have peer review where people do this, but sometimes people see things that other people don't see. And this is another benefit of the peer review system, because technically, even though this calculation looks correct, and everything looks good, mathematically this calculation is actually wrong. And so this is a point Jackson brought up, is this 18,000 gallons. I calculated the amount of chlorine based on having a pool that's 18,000 gallons, but what happens if I dump more liquid into the pool? What happens to the volume? It goes up. So by adding this chlorinating solution, the volume is not 18,000 gallons anymore. The volume is 18,000 gallons plus 0.9 liters, or about 1 liter. And that means that I shot for exactly 1 ppm, but in actuality, it's going to be a little bit less than 1 ppm because I have a little bit more volume. And so my calculation is wrong. And so we do 2 things in that case. Option 1 is we take the easy way out. The easy way out is to save ourselves some math. The easy way out is we make an assumption. We assume that 18,000 gallons plus 0.9 liters is about 18,000 gallons. And so in other words, we're going to say, even if I dump a liter in there, it's not going to change the volume significantly. And if I think about it, there's 4 liters in a gallon, so this is like a 1/4 gallon, less than a 1/4 gallon. Or actually more than a 1/4 gallon, because it's less than 4 liters. And so this is, but even if it's a 1/4 gallon or a 1/3 of a gallon, let's say, is it really going to change the volume of the pool that much? No. And so what we can say is, yes, our calculation's not accurate, but it's close enough that it's not going to make that much difference. Does that make sense? But what happens if you buy, let's say, I don't want to buy the concentrated. I'm going to buy the dilute chlorinating solution. So let's say rather than your chlorinating solution was 7%, let's say your chlorinating solution was 7 parts per million. If your chlorinating solution were 7 parts per million, how many gallons are you going to be dumping in there? A huge number of gallons. And that's going to result in a significant change in the volume. And so this works fine. Okay, let's say I add 1 more gallon. It's close enough. 2 gallons. But what happens if I had to add 100 gallons? What happens if I had to add 1,000 gallons? Is my calculation still going to be accurate? No, it's going to be way off, this calculation. And so what we're going to do, and in this class, is we're going to do, this is an advanced problem, and this is the advanced level, but we're going to take it one more step advanced. The one more step advanced is, in addition to the conversion factor method or dimensional analysis, we're also going to do system of equations in solving problems. System of equations would be, the hardest system of equations that we're going to solve in this class will be two unknowns and two equations. And so the two unknowns is, what's the final volume of the pool? The final volume of the pool depends on how much chlorinating solution you dump in, right? Well, what's the volume of the chlorinating solution? Well, the volume of the chlorinating solution depends on the final volume of the pool. And so you have this problem, you know, the chicken or the egg. You know, how are you going to figure it out? And so in that case, we have what we call a system equation. In order to figure that out, we have two unknowns. We don't know what the final volume of the pool is, because in order to get the final volume of the pool, we need to know the chlorinating solution volume. In order to get the chlorinating solution volume, we need to know the final volume of the pool. So we're stuck. And we have two unknowns. We don't know the volume of the pool, we don't know the volume of the chlorinating solution. And so when we're stuck like that, what we do is we try to think of two equations and then combine them. And so let me, and it turns out it's not hard for this particular one. And so doing this correctly doesn't require that much more work. So we don't know the volume of the pool. The volume, okay, this is factoring in, you know, without assumption. Actually, this, let me just say without assumption. With the assumption, it just speeds things up. We don't have to do that. But the volume of the pool is going to be 18,000 gallons plus, I'm going to call the variable X gallons of chlorinating solution. And here we don't want to calculate liters, so we're going to have to go from liters to gallons of that. Okay, then, well, I need to calculate how many gallons of chlorinating solution I need. And so what I'm going to do is I'm going to substitute this into the original equation. And so we're going to start off with a new volume. The new volume is going to be 18,000 gallons plus X gallons, or 18,000 plus X. And then we get rid of the gallons. We go from gallons to liters, and then etc. Liters to milliliters. And this whole thing is going to equal X gallons of chlorinating solution. And so what I did is I just substituted in this and got it in terms of one variable. The variable is X, and then solve this equation for X. Solving this equation for X is not hard algebraically. Sometimes solving for X is hard algebraically, and we have to use a method of successive approximations. Do you call the method of successive approximations? Another word for, or another name for the method of successive approximations? It's in Appendix A. A method of successive approximations is like this. 2x is equal to 6. 2x is equal to 6. I'm going to guess x is 2. So 2 times 2 is 4. Oh, I'm a little small. So I'm going to guess x is 2.5. 2.5 times 2 is 5. It's still too small. Then I'm going to guess x is 3. 3 times 2 is 6. Oh, I got it. So I got it in 3 guesses, or 2 guesses. That's the method of successive approximation. So when it becomes hard to solve for x, then we do that. But this is not hard to solve for x. And so this is not much more work, and you can get an accurate answer. This answer is incorrect. But how incorrect is it? Well, this is livable incorrect, because it's going to make very little change. In fact, you know what the volume is going to be to 1 sig fig if I use this? The same. It's going to come out 0.9 liters. It's not going to make any difference. Okay. Now, if I had to add thousands of gallons, then they're going to be totally different. All right, so this is another method that, and there are maybe about, I don't know how many homework, I forgot how many homework assignments I assigned with 2 equations, 2 unknowns. Maybe 5 or 6. And so this is 2 equations, 2 unknowns. And so some problems are going to be algebraic, like temperature. Some problems are going to be unit conversions, like this. And well, temperature also has a unit conversion too when you're looking at temperature changes. I forgot to talk about that. But maybe we'll hit that in LAM. All right, any questions on this? Okay, what I'm going to do now is leave chapter 1 and move on to chapter 2. These are from the website for the book, but these are chapter objectives here. Describe and distinguish between the law of conservation of mass, the law of constant composition, and the law of multiple proportions. Most laws come from where? Most laws come from theory, or most laws come from observations? Observations. 2 of these came from observation, 1 came from theory. Do you know which 2 came from observation? Which 1 came from theory? Yeah, the conservation of mass came from observation, and constant composition came from observation, but multiple proportions came from theory. Discuss the discovery of electrons and describe the basic properties, their basic properties, such as charge and mass. Do you know who discovered the electrons? This isn't necessarily a history class, so I don't expect you to know the names and the dates, this type of stuff. But there are some important names. J.J. Thomson was credited for discovering electrons. We'll talk about the charge and the mass later. You know, we want to know how much does an electron weigh, what's its charge, and how big is an electron. Do you know how big an electron is? Uh-huh. Not very.
Would it be wise to build a study guide off of this for a quiz?
Yeah.
So like this is the information that I should expect participants.
Yeah, these are the key points in the chapter. So we'll just briefly go through this first, and then we'll look at the chapter. Identify the features of the nucleus of an atom and discuss the properties of protons, neutrons, and electrons. Describe the meaning of isotope and discuss how the masses of all the elements were deduced. Well, I guess deduced, you could use that word, but I would just, you know, the masses of an atom, like for example, you guys already know that atoms are made up of what? Protons, neutrons, and electrons. So if I have 9 protons and 10 neutrons and 9 electrons, do you know what atom I'm looking at? 9 protons, 10 neutrons, and 9 electrons. What atom? What element? Fluorine. And did you know that all the fluorine atoms in nature have the same? There's only what we call one isotope of fluorine naturally occurring, and that's fluorine 19. 9 protons, 10 neutrons, 9 electrons. And do you know we know the mass of a proton, we know the mass of a neutron, and we know the mass of an electron. We have those masses. Can we just add up the masses of the protons and neutrons and electrons? So 9 times the mass of the proton, 10 times the mass of the neutron, 9 times the mass of the electron, and then just add those up to calculate the mass of the fluorine atom. Can we just do that? It seems to make sense. We just combine the masses of the protons, neutrons, electrons, and we get the mass of fluorine. But it doesn't work. It doesn't work because there's something called the mass. Does anybody remember this from before? The mass defect. Have you heard of the mass defect before? No. Because of the mass defect, we can't calculate the masses of the atoms. What we have to do is we have to weigh these. And do you know how we weigh them? You know what we use to weigh atoms? What instrument we use to weigh atoms? We don't call it a scale. It's kind of like a scale. We call it a mass spectrometer. And so we use a mass spectrometer to measure the masses of the atoms. Let me see what happened. So, and these are the things we'll be talking about in this chapter. Let me just go ahead and put this in. Shoot. And so we weigh isotopes with a mass spectrometer. Determine the atomic mass of an element from experimentally determined masses in percent abundances. So the atomic mass is the average of all the isotopes. So we just calculate the weighted average, what we call it, to figure out the average mass. Identify different regions of the periodic table, including metals, nonmetals, noble gases, metalloids, transition metals, main group elements. Identify the value of Avogadro's constant and describe the meaning of molar mass. Use Avogadro's constant to convert. And so these are more dimensional analysis problems here at the end. And so for me, the key points here would be atoms, just the theory of atoms, structure, properties, this kind of stuff. And how to weigh the atoms, and isotopes, isotopic masses, average atomic masses, Avogadro's number, that type of stuff. So let's take a look at this chapter. The first thing is atoms. There are two competing hypotheses. One hypothesis was that matter was not infinitely divisible. There's a limit. And so you could break matter into smaller and smaller pieces, but ultimately you're going to hit a piece that can no longer be broken apart into smaller pieces, and that piece would be the atom. So if we took an atom and then tried to break it into a smaller piece of the element, it doesn't work because it breaks up into subatomic particles, protons, neutrons, and electrons. But they didn't know about protons, neutrons, and electrons at this time, but that was one of the hypotheses. What was the other hypothesis? Was it phlogiston? Yeah. Well, the phlogiston was part of the chemical reaction stuff, and that was for the conservation of mass. The phlogiston was like this ether, and so if a candle burns, what happened to all that mass? Well, it went into phlogiston, and so it's still there, but the phlogiston. And the phlogiston might not even be mass. Actually, it wasn't with the conservation of mass. It's just what happened to the candle, and it went into phlogiston, that kind of thing. But this is a little different. This is looking at matter. And the other thing of matter is, you know, we can have a smaller and smaller piece of gold. In fact, we can have an infinitely small piece of gold. And so either we're going to have the smallest piece of gold is going to be a single atom, or the smallest piece of gold is just going to be an infinitely tiny particle of gold. And so what is it? Well, I know, like in middle school, I was taught that atoms exist, that matter is made up of atoms. But in science, you know, if you have two competing hypotheses, which one is going to gain acceptance? The one that's going to gain acceptance is the one that has good supporting evidence, right? And so what evidence do you have for the existence of atoms? So let me tell you, let me ask you this. Do you believe in atoms, yes or no? Yes? Okay, give me proof, because let's say I'm a skeptic, and scientists are supposed to act as skeptics. I'm a skeptic, I don't believe in atoms, prove it to me. So what are you going to give me as proof? You know, because, and I need proof. I need good, solid proof that atoms exist. So can you give me some good, solid proof that atoms exist? Because I've never seen an atom. Now, I've seen pictures and cartoons of atoms, but can you give me one piece of proof? How do you know? You know, or how can you prove it to me that atoms exist? Uh-huh.
Radioactive isotopes might be pretty good. Like put that in measures. Weigh it. Let's say it's super radioactive, like has a really quick half-life. Well, you weigh it really precisely, leave it undisturbed for like however long, and weigh it again. It's gonna weigh slightly less because it's going to decay, right? Is that correct?
Okay.
It's really hard to explain that if you control for the other factors, how that happened without radioactive decay. Is that right?
Well, you could have radioactive decay, but couldn't matter also be infinitely divisible and still give you radioactive decay?
It'd be a lot harder to explain that.
Well, then, I mean, because you have to think, well, there are two contexts we can do this in. One, we could do this back in the time. Do you know where early atomic theory? Well, atoms were proposed, I don't know, centuries ago, maybe. But the first meaningful atomic theory was with Dalton. And Dalton was in, what, the late 1700s, 1800s, so 18th, 19th century, something like that. And if we think about it, yeah, they could have done radioactive decay, but I'd have to think about that to see how that does. I would see how it could because of proportions, you know, and if they could measure what's coming off there, then they could do it that way. So I guess you could argue that radioactive decay, yeah, and then just show me some evidence for that. What else could we have? And so in science, this is, you know, this is, I guess, another of the purposes. The purpose of science is if you propose a hypothesis, you want some supporting evidence for that hypothesis, right? You want to see some observations. And sometimes that supporting evidence is solid. Like nowadays, you know, the people who don't believe in atoms would be ignoring a mountain of evidence in support of atoms. In fact, atoms have been observed. That is, with modern instruments, you can see atoms with a scanning tunneling microscope or scanning electron microscope. And this is an image of the atoms here. And you can manipulate single atoms, like IBM. IBM created a logo, and they created a little child animation by manipulating the atoms. And if you take these atoms and then try to smash them into smaller pieces using an atom smasher, they don't smash into smaller atoms. What they do is they smash into subatomic particles like protons, neutrons, and electrons. So in modern times, you know, and not only can you see them with microscopes, you can see these with X-rays as well, you know, with the X-ray diffractometer, etc. And so there's a huge amount of evidence in support, evidence being observations in support of atoms. Right? And so atomic theory has gained widespread acceptance. But if we think back in Dalton's time, Dalton didn't have sophisticated instruments in the late 1700s. And so what was Dalton's proof? You know, and of course there are harsh critics of Dalton, you know, people who didn't believe in Dalton's atomic theory. And so they wanted good solid evidence. And do you know what the good solid evidence he provided was? This. And so this is why, you know, even though atoms were proposed, I think, by Greek philosophers centuries before this, this is why Dalton's credited with atomic theory. Dalton's credited with atomic theory because he offered supporting evidence for the existence of atoms. And what was the supporting evidence? The supporting evidence was the law of conservation of mass. The law of conservation of mass is that if there's a chemical change, for example here, in this precipitation reaction, we mix these two chemicals together. We start off with 104.5, we end up with 104.450 grams. And so the mass didn't change before and after the chemical reaction. And so in Dalton's atomic theory, what he said is that in chemical reactions like this, the atoms just get rearranged. And so we don't lose any atoms, we don't gain any atoms. So atoms are neither created nor destroyed. They're just rearranged in chemical reactions. And that would explain the conservation of mass. But you say, well, even if matter was infinitely divisible, wouldn't you still have conservation of mass? Then yes, you know, that could be argued too. And so this isn't complete. However, another observation is consistent with atomic theory, and that is the law of constant composition. The law of constant composition is this. The law of constant composition says that, for example, water has a fixed composition. What's the composition of water? H2O. And in California, it's H2O, but can you buy like H2O light? Like say I'm on a diet, I want a little bit less oxygen, you know, a little bit more hydrogen. Hydrogen weighs less. Could I buy H2O light, you know, with a little less? Maybe rather than one full oxygen, I'd like H2O.9 or H2O.8. Is that possible? Or maybe on the reverse, maybe I want a little bit more hydrogen, you know? Is it possible to have H2.2.1? And so the situation is this. If you're mixing, let's say you're making some cookies and you like lots of sugar. So you take 2 parts of flour, or actually, let's reverse it. Let's take 2 parts sugar, 2 cups of sugar, 1 cup of flour. When you mix 2 cups of sugar and 1 cup of flour, are you always going to get exactly 2-to-1 ratio each time? No. But with water, if you buy water in LA, pure water, the pure water I used, this wasn't pure enough. The pure water I used when I was a researcher at UCLA, I didn't use it at UCSB, I didn't need that pure water. But I was doing some experiments where I needed extremely pure water. Extremely pure water was actually in the psychology building, so I'd have to wheel a cart over the psychology. And then they had this on the wall. They had deionized water going into a distillation apparatus, and so it's distilled once. Not only is it distilled once, it's distilled twice. So it's called doubly distilled water, and it's called DD water, or doubly distilled water. So I use DD water, and then it's hit with UV. UV is radiation under 390 nanometers. So anything under 390 should kill things in there. And they have, you know, near UV far, or I shouldn't say like UVA, UVB, UVC, depending on how close it is to 390, you know. But anyway, if I get pure water here, DD water, double D water in LA, is it the same as double D water in New York, or does New York have a little bit more hydrogen or a little bit more oxygen? Are they the same, or is it different? It's the same. It's 2-to-1, hydrogen to oxygen. It's always 2-to-1. And so that's another observation that supports atomic theory, because if matter were infinitely divisible, it'd be like mixing flour and sugar, you know? You might get an extra grain of sugar or an extra grain of flour. And so the composition isn't always going to be the same when you're making.
Am I to believe that that's the same price that wrote War and Peace, or no relation?
No, I don't know.
Timing somewhat, or is that
Maybe a relative? I'm not sure. Maybe because it's, you know.
The timing works out.
Yeah. Yeah. That's a good question. I don't know, but probably on Wikipedia. Probably take a look there. But anyway, these two, because well, getting back to this, and maybe I'll take a look at that during the break, but when we mix these two together, and making water is just mixing hydrogen with oxygen. And if matter were infinitely divisible, you might be a little high in one and a little bit low in the other, right? And that could easily happen, but that's not what's observed. And so theory should explain the observations. Well, atomic theory does explain these observations, or describe these. You know, it doesn't necessarily explain, it describes these observations. And then theories should do one more thing. What should a theory do? Predict. And Dalton's atomic theory predicted the law of multiple proportions. The law of multiple proportions just says that in compounds, atoms combine in simple whole number ratios. So the law of multiple proportions here says carbon and oxygen will combine in simple whole number ratios, 1 to 1 or 1 to 2. And this was observed using masses because in those times they didn't analyze it using atoms or things that can observe atoms like X-rays or whatnot. They looked at the masses. So here it's a 1 to 133 ratio. Here it's a 1 to 266 ratio. So it's a 1 to 1 and 1 to 2 ratio. So if we had 3 parts of oxygen, it would be 3 times this. 4 parts of oxygen would be 4 times this ratio. And so based on that ratio, that's the law of multiple proportions, and it was successfully tested. All right, so we'll stop here and we'll take a break. We'll take a 15-minute break. So Dalton's atomic theory, most of this you already know. You don't have to memorize any of this. Each chemical element is composed of minute individual particles called atoms. Atoms can be neither created nor destroyed in chemical changes. In chemical changes, the atoms get rearranged. In nuclear changes, the nucleus breaks apart. Either chunks of it break apart, or nuclei, if you get 2 atoms and you smash them together, sometimes the nuclei can fuse together. So we could have fission reactions where they break apart, or fusion reactions where you fuse nuclei together. 2, all atoms of an element are alike in mass. Well, this is Dalton's. This is not true anymore because we know of isotopes. So, for example, if you drink water, do all the water molecules in a glass of water, I'm not sure if this is water, like I said, but this is probably water, weigh the same amount? Do all the, so if I grab, if I had a molecular size, a pair of tweezers, and I grab any water molecule out of there, it would weigh the same as any other water molecule in there? Yes? Or no? No?
Do you count isotopes?
Yes? We have to count isotopes because, yeah, we have to count isotopes. We have to count isotopes because if you grab an individual water molecule out of there, it depends on what isotope it is. And so, no, they don't. And so we have, I don't know, do you know how many isotopes of hydrogen there are? And do you know how many isotopes of oxygen there are? No. If we knew the theory, that's a great thing. This is why scientists ultimately want to understand the theory, because did I forget to record this? Oh, no, I didn't. If we know the theory, then we can predict things like that. If I want to know how many isotopes there are, I just use the theory and then predict it. Otherwise, I'd have to go in and just measure it. And do you know what we do now? What we do now is we just go in and measure it. I don't know how many. And so that's what the theoreticians have to figure out. But that's more nuclear chemistry, not chemistry. What's happening with the nucleus. How many protons. In each of their compounds, different elements combine in simple numerical ratio. We call that the law of multiple proportions. For example, 1 atom A to 1 atom B, or 1 atom A to 2 atoms B, like CO, CO2. Okay. So here's the law of multiple proportions. That's basically it. Chemists aren't so interested in the nucleus, because in chemical reactions, what gets rearranged are just the atoms. And so what chemists are interested in, as far as the forces of nature go, do you know the forces of nature? Did I already ask you this? What are the forces of nature, say? It's like gravitational force. Are chemists most interested in gravity? Like, what's holding the water molecules together here? Is it gravity? The liquid is to the bottom of the container. The liquid sinking to the bottom of the container is gravity. So are chemists most interested in gravity? Not really. Chemists are most interested in The strong force, the nuclear strong force. You know, nuclear strong force, you know, with the quarks. You heard of the quarks? Protons are made up of quarks and neutrons made up of quarks. You heard of that? We don't have to go to the quark level, the subatomic level. We just go to the subatomic level. You know, protons, neutrons, electrons is enough for us. So we don't really care about the strong force. And have you heard of the nuclear weak force? We care about the nuclear weak force because the nuclear weak force is what holds the nucleus together. What holds the nucleus together is called the nuclear binding energy. And this is why we can't combine the masses. Because let's say the nucleus of a fluorine atom consists of 9 protons and 10 neutrons. If we combine the masses, it ends up weighing more than the actual nucleus. Because what happens is this. What happens is some of the mass of the nucleus is converted into energy, the nuclear binding energy. And so we have to weigh atoms. We can't just add up the parts of the atom and determine the mass that way. And so the nuclear binding energy is this. It's delta E, which is the NBE, called the nuclear binding energy, and that's equal to delta M times C squared. And so this would be the nuclear force, or the nuclear weak force. Although it's weak, the nuclear weak force is a heck of a lot stronger than the electrical force is shown down here. This is electric. And so some of the mass of the nucleus is converted into energy. Now, if we always had the same proportion of mass converted into energy, then it would be easy to figure out. But the proportion of mass that's converted into energy, you know, what percent of the mass of the nucleus is converted into energy to hold the nucleus together, isn't a function of how many, what we call nucleons, protons and neutrons there are in the nucleus. It's a function of how strong the nucleus is bound together. So some nuclei are exceptionally strong and stable, helium, neon, etc. Other nuclei are exceptionally weak and unstable, uranium, plutonium. Those nuclei are very weak, and so the proportion of nuclear binding energy there is very small, and so those nuclei are weak, unstable, and prone to breaking apart. And so, anyway, because of the nuclear binding energy, we can't just add up the masses. We know what the proton weighs, we know what the electron and neutron weighs, and so we should just be able to add up the masses, but they don't add up. And that's called the mass defect. And so the mass defect prevents us. And so that's the only nuclear force we're interested in. The nuclear force we're interested in results in the mass defect, which means that if I know that fluorine contains 9 protons, 9 electrons, and 10 neutrons, then I can't just multiply the masses of those out and add them up. They don't sum up. And so we take 9 times the mass of the proton, 9 times the mass of the electron, and 10 times the mass of the neutron, and we sum those up, and that does not equal the mass of fluorine. In fact, the mass of fluorine is a little bit less. The mass of fluorine is a little bit less because some of the mass of the nucleus was converted into the nuclear binding energy, which holds the nucleus together. Because if we didn't have the nuclear binding energy, what happens when we have like charges? Do like charges attract one another, or do like charges repel? They repel each other. And in order to force them together, that requires some energy. And what is that energy? That energy for the nucleus is going to be the nuclear binding energy. And so we're going to cram a whole bunch of protons into the nucleus and hold them together. Now, if we had electrons in the nucleus, then that could hold it together too, because, you know, protons and electrons would attract one another. But we don't. And these are 2 neutral particles. But anyway, as far as nuclear forces go, we're only interested in the mass defect. As far as electrical forces go, electrical forces are what chemistry is all about. And so chemists are only interested in these electric forces. The electric forces hold, you know, the water molecules together. So I don't know if anybody saw the videos that I posted on the page, or the fountain You know, there's a fountain in downtown LA that shoots these gigantic drops of water. And these drops of water look like blobs, and you can watch them, you know, contort into different shapes as they're being shot out. It's a pretty amazing fountain. Okay, so it's not just electric. We primarily chemists are interested in electric forces, but we also have to worry about magnetic. Electric, electric and magnetic forces go hand in hand. We call it electricity of magnetism. And so they can interact in this way. So if I have a charged particle that's moving, they can be deflected by magnetic fields here. So positive charge can be deflected up, and negative charge would be deflected in opposite directions. So, they're deflected that way. And so this interaction is important. In fact, you know, we can generate electricity this way by moving the magnetic field on a wire, coiled wire, to generate a flow of electrons. All right, so that's a little bit of background for this. Do you know what this thing is called? The cathode ray tube. This is called the cathode ray tube, or the CRT. And what this does is generates a beam of cathode ray, a cathode ray beam. And the cathode ray beam is this. This beam, you know, when we have a battery here, or power supply, essentially what we're going to do is apply voltage and crank up the voltage. This tube is sealed, and so usually put a low pressure gas in here. Crank up the voltage and you start generating these cathode rays. And the cathode rays are going to be shot towards this plate here, which is called the anode. This anode has a positive charge, so they're attracted to this positive charge, and then they go over here and hit the detector. And the cathode ray actually turns out to be electrons. And so cathode rays are a beam of electrons. And the electrons are a fundamental part of all matter. That is, cathode rays, which are electrons, and these cathode rays and electrons are a fundamental part of all matter, as determined by who? Do you know the person who discovered electron? Their name? Kiana? Yeah, J.J. Thomson. J.J. Thomson, and normally I don't make you remember names, but I was looking at some tests and they asked for the name. So, on some standardized exams, they think it's important. And so J.J. Thomson discovered the electron. How did he discover the electron? He discovered it using a cathode ray tube. And you think, well, it depends on what the cathode is made up of. A typical cathode in a cathode ray tube is made up of aluminum. And the way he determined that electrons are part of all matter is he changed it. So instead of using aluminum, what if you used iron? So if you used an iron cathode, you get the same cathode rays. If you used a steel cathode, which is a mix, you know, steel is a mix of different elements, primarily iron, you get the same cathode. If you use a graphite electrode here, we call the cathode an electrode, you get the same cathode. So no matter what J.J. Thomson put, what material he put here, he got the same cathode ray. And so what that meant was that cathode rays, i.e. electrons, are present in all matter. Although he couldn't put an insulator here. If you put a piece of glass, you aren't going to generate the cathode ray. That, you know, he just extended it to that. All right. So electrons are a fundamental part of all matter, and that was, you know, what evidence was in support of that? The evidence that was in support of that was changing the cathode material. Now, the electrons are negatively charged. What evidence is in support of negative? The observation is that the electron beam gets attracted to this positive plate, so a lot of them hit this, but some of them go through this hole. If you put a piece of metal here, the metal will acquire negative charge. You can measure that. And so we know that this beam consists of negatively charged particles, and they can hit this detector here. And so that was the discovery of the electron. You can't see that this is invisible, the cathode ray, but you can make it visible by putting a phosphorescent coating on the inside of the glass. And the phosphorescent coating will give you a color, a glow to it. When the electrons strike it, it starts to glow. We have a cathode ray tube. I'll show it to you. Next day. Now, if these are negatively charged particles, they're going to interact with electric fields here. And essentially what we have is this. It's a beam of electrons, and what this is a lightning bolt. It's a controlled lightning bolt. A normal lightning bolt, you'll see, there's a voltage, high voltage between, the clouds and the earth, and that, like, you crank this up, you generate a lightning bolt. But this is a very straight lightning bolt. When you look at the lightning bolts in the sky, they're very jagged. They're very jagged because they have a lot of collisions. And they have a lot of collisions because the gas pressure and the density is much higher. Here we have a low pressure gas, that's why they call them an evacuated tube. And so it's mostly empty space, and so there are a lot fewer collisions. So it's a controlled lightning bolt, which just goes through here. Well, this lightning bolt of electrons, we can do different things. We put another plate here, and so we'll put a cathode and anode here. You don't have to worry about the names of this, but later on you might. And we'll just apply a voltage. This voltage here is not going to be big enough to generate another lightning bolt. We'll keep the voltage lower. And we keep the voltage lower, then what can happen is it can deflect the beam of electrons. If we make the voltage too high, not only will we get a lightning bolt here, but the beam of electrons will hit the positive plate. And so this is just enough voltage to deflect it. And so we see a deflection here in the beam using electric field. Electric field, we're going to have to put some kind of power supply there. If we use a magnet, then this doesn't require any electricity. You can just put a magnet there, and the magnet will do the same thing. It'll deflect it. Negatively charged particles get deflected down like this. Positively charged particles would get deflected up here. And so, deflection. Now, based on the deflection here, you can ignore this one, because here what they're doing is they're canceling out the electric field with the magnetic field. And so it's just going straight here. The angle of deflection depends on how heavy the particle is. And so for very light particles, they're easily deflected. Electrons are very light, they're easily deflected. And so we don't have to apply too big of a magnet here or too big of an electric field here to deflect these. These are really easy to deflect because they're so light. So that's the discovery of the electron. And what I'm going to do here is I'm going to jump ahead. How do you determine the mass of an atom? How we determine the mass of an atom is by using something that looks similar to the cathode ray tube. Except rather than having a beam of electrons, the cathode ray tube has a beam of electrons. In this instrument is called a mass spectrometer. In a mass spectrometer, we have a beam of atoms. And the beam of atoms are shot out. And the problem is beam of atoms are normally neutral. So what we have to do is we have to ionize them. So we get a cathode ray gun and shoot electrons at this. When you shoot electrons at this, you can knock electrons off atoms, right? In other words, an electron gun. We can have an electron gun here, or we can have a chemical beam. A chemical beam shoots small molecules or atoms at it. So this is the same kind of concept as this. So what we do is we have atoms here, and then we charge the atoms. When we charge the atoms, this will be a stream of positive ions. Then we put a negative plate here. The atoms, now ions, are going to be accelerated to the negative plate. And then we put a magnet here. This is a magnet. And what's going to happen is the light atoms, they have lower inertia and they get deflected more. Whereas the heavy atoms are heavier and they aren't deflected as much. And so what we have here is we can spread out the atoms based on their weight, on their mass. And so the light ones strike over here and the heavy ones strike over here. And so this is how we can weigh atoms. But when we weigh atoms, we need to do something. Like, for example, if you're going to weigh something on a balance, what's the first thing you do before you even use the balance? Well, you would tear it, but not only you'd tear it, before even tearing it, you'd make sure that it is properly calibrated. And so the first thing we do is we got to calibrate it to make sure it's reading correctly. And so we need something to feed in here to make sure it's giving us the correct reading. Now, what is it? what's the standard for mass? The standard for mass used to be a chunk of metal, platinum palladium metal, that weighs exactly 1 kilogram, because somebody said this weighs exactly 1 kilogram, person who defined it. And the person who defined it says this piece of metal weighs exactly 1 kilogram, and therefore this is the standard for that. Do you think we could fit that chunk of metal into our mass spectrometer here? It would be great if we could. You shoot the 1 kilogram mass, and then where it hits the balance, we call that exactly 1 kilogram. But it's not going to fit in this, unfortunately. And not only that, the metal's locked in. Where's the metal locked in?
There it is.
Yeah.
Well, they make copies.
They made copies.
So everything.
Actually, we have copies too, but are the copies as good? Do you think the copies are good to the nearest atom? Probably not. They're close. Depends on how much money you want to spend. You probably can get a pretty good one. We have cheap ones. Our copies, we have clones of it, and we use those for calibrating our balances. And I think they cost a couple $100. So that wasn't that much.
We have that silicon sphere now.
Hmm?
We have that silicon sphere now, which is supposed to be a bit better.
Yeah, and actually they have something that's accessible to everyone. You know, not everyone has a key to the vault, but now they're using an electric field. Have you heard of the electromagnetic field to determine the mass? And so they apply a certain field level and applies a certain force, and then they call that exactly 1 kilogram when they get the right force on that force field. Anyway, we can't feed kilogram mass in here, so what are we going to use to calibrate this balance? Is there something else? Well, number one, we aren't going to weigh atoms in units of kilograms. Normally we weigh atoms in units of what? Grams? No, it's like 10 to the minus 28 grams or something like that. Normally we don't weigh atoms to the nearest gram. We weigh atoms using what unit? Microgram? Nanogram? Picogram? What's smaller than pico? Femto? Femto's still too big. What's smaller than femto? Atto? Atto's still too big. So what should we do? We need to learn a lot more prefixes, right? But no, we're going to give up on those. We're not going to measure it in attograms because it would be way too big of a number of or not way too big. It would be way too small of a number, 0.000 whatever attograms. We don't want to work with that many decimal places. So we define a new calibration standard. And you know what the new calibration standard was? In the 1950s, the new calibration standard was oxygen 16. So they take an oxygen 16. Oxygen 16 consists of 8 protons, 8 neutrons, and 8 electrons. And that gave us oxygen 16. So what they do is they feed an oxygen 16 atom in here, and where it strikes the detector, they type in exactly 16. And what are the units for atoms? AMU, atomic mass units, or U. And so the mass spectrometers used to be calibrated with oxygen 16. Well, oxygen 16 is a little bit of a hassle because oxygen is a gas. Gases are mostly empty space. And not only the gases are, like air is impure. And so after the 1950s, they changed the standard. And so if you're at a garage sale or something like that, and somebody's selling an old periodic table, don't buy it because all the masses are wrong. They're based on oxygen 16. And so they changed it from oxygen 16 to the new standard. The new standard is carbon 12. And carbon 12 is a hassle because it's a solid. Well, it's not really too much of a hassle. So what you do is it's cheap. You can buy a pretty pure graphite. And graphite consists of 2 carbon isotopes, carbon 12 and carbon 13. And it's like 99% carbon 12, so very little carbon 13 in there. So what you do is you strike it with a laser, and what the laser does is it vaporizes carbon atoms off the surface. And these vaporized carbon atoms, then you hit it with like an electron gun beam and ionize them. So you have these carbon cations here. And so carbon 12 strikes the detector, and then we know, okay, we tell the computer that's exactly 12U. Exactly. How many sig figs? Infinite sig figs. And then, based on physics, you know, carbon-13 has more inertia, and therefore it's going to strike a little further out. And based on the physics, how far out it strikes, we can determine the mass, its relative mass. And so mass spectrometers we can calibrate with carbon-12, or once we know the masses of other things with great precision, we can calibrate it with any of them. Okay, now a mass spectrometer is great because it tells us three things. One, let's say if I have a sample of mercury, it tells us the number of isotopes. It turns out mercury has 1, 2, 3, 4, 5, 6, 7 different isotopes. That's hard to predict using theory, unless maybe the theoreticians have an easier way of predicting it. But mercury has 7 isotopes. 2, they tell us the intensity of the strikes. You know, this isotope, there's not that many hits, whereas this isotope, there's a lot of hits. And based on those, we can graph those. So based on the relative height, you know, this one's the most abundant. And we can get a very precise mass. That's 3. We can get a very precise and accurate masses if this is properly calibrated. We can get 6 sig figs or more on the mass. It's not showing it here because it would be way too many digits. But this is around 202. There's a mercury 202 here is the most abundant. And we can get the percent abundances based on normalizing this to 100%. And so mass spectrometer is the way we're going to determine the mass of the isotopes and the number of isotopes. And then on the periodic table, we have the average mass of all the isotopes. For mercury, it's 200.59, so about 200.6 is the average. Which makes sense, because if 202 is the most abundant and we add this shoulder over here, then the average of all these, the weighted average of all these is around 200.6, right about here. Do you see that? That would be the average of this here. You can see at 200.6 there are no atoms that strike there. That's because it's the average, not the individuals. So that's the mass spectrometer, and that's how we get isotopic masses. We don't get isotopic masses by adding up the masses of the protons, neutrons, electrons because of the mass defect. We get the masses by feeding them into a mass spectrometer and weighing them. So it's kind of the same physics of the cathode ray tube. The cathode ray tube, J.J. Thomson, do you guys recognize this experiment? This is a pretty crude drawing. Do you know what's inside this bottle here? Oil. They have one of these at Griffith. Years ago I went there and I watched it through the telescope. And when you want it, this is an atomizer. So what they're trying to do is they're trying to spray the oil to get consistent sized drops. They want tiny droplets. And hopefully all the droplets are about the same size, which they are from the atomizer. And then what they'll do is they'll have a radioactive source over here, and the radioactive source shoots things like high energy light or whatever, chunks of nuclei. And it hits these droplets, or hits the air. It actually hits air molecules and ionizes those. And what happens is we generate free electrons. Those free electrons will stick to the oil droplets. And these oil droplets are kind of big compared to an electron. You know, I asked you how big an electron is, and you said very small. That's correct, very small. But you know how big it is in size? Is it like atometer small? Smaller than atometer? I don't know what's after atto. And actually, you can keep going down the metric prefixes, but you're going to run out because electron size is 0. And so how can an electron have a size of 0? And so that's very bizarre. And so we'll talk about that later. But anyway, this generates electrons. The radioactive source over here generates electrons. These electrons get stuck to the oil droplets. And different numbers of electrons can get stuck. So what happens if an oil droplet accumulates a large number of electrons, what we have is a competition between electrical forces and gravitational forces. Gravitational forces are pulling the droplets down. Electrical forces will be pulling the charged droplets up because the charged droplets are going to be negatively charged. So the more electrons you have on there, the more the electrical forces are going to be important. And the fewer, like for example, if we had 0 electrons, they'd just drop naturally due to gravitational forces. And so based on looking at the whole array, you know, and when you do this, when you go to Griffith and look through the telescope, you'll see some droplets going up, some droplets just stationary in space, and other droplets dropping down. When you look at the whole array, the distribution, then what this person got, and who was this person who did this? This is called the blank oil drop experiment, Millikan. And what Millikan got was he got the fundamental charge on electrons. So he figured out the number of electrons that get stuck here are going to be in integer multiples. And the smallest integer was going to be 1 electron. And that 1 electron is going to have a charge of minus 1.6 times 10 to the minus 19 coulombs of charge. And if you have 2 electrons, it'd be double. 3 electrons would be triple that charge, etc. So Millikan got the charge on an electron. So J.J. Thomson discovered the electron. Millikan got the charge on the electron.
I think I must have missed something. Why oil?
Why oil?
Relevant property.
No, it's just oil is just fairly inert. I mean, chemically, so it's not going to react with anything. And then it's easy to get small droplets. And oil is something that's in the lab. A lot of labs will have a bottle of mineral oil sitting on the shelf. In our lab, we had lots of different oils. I had silicone-based oils and carbon-based oils and different, mostly for the pump. And so we have lots of oil in the lab. So probably they just had oil in the lab. Otherwise, it's hard to get things to have a consistent. I mean, I guess he could have used like flour, you know, and got really, really finely divided flour. That would have worked probably too. You know, anything works. Well, how did he get the electrons? He used the radioactive source. Radioactive atoms have unstable nuclei. They have weak nuclear binding energies. Some of these, when they decay, they're kind of high energy. When they decay the lower energy, the energy is conserved. That's another law. This is a law of thermodynamics. Energy is neither created nor destroyed. So if energy drops, something has to happen. And usually what might happen is high energy light's emitted, X-rays and gamma rays. You know, high energy light radiation. We'll talk more about that in chapter 8. Other things that might happen are the nuclei might break off chunks. Maybe the nuclei are a bit too big, and so chunks a bit. And so a chunk would be an alpha particle. An alpha particle would be like 2 protons and 2 neutrons. 2 protons and 2 neutrons would be equivalent to a helium nucleus. And so that's why they call alpha particles He2+. There are no electrons that break off. There are no electrons in the nucleus. And so we have X-rays, gamma rays, and alpha particles. X-rays, gamma rays, and alpha particles are the 3 most dangerous forms of radiation from radioactive atoms. Which one do you worry about the most? Oh, we worry about all of them. Like X-rays, we want to protect ourselves from X-rays. To protect yourself from X-rays, you would use lead sheet. For gamma rays are higher energy, so you use lead brick to protect yourself. Because X-rays and gamma rays are very penetrating radiation, and lead helps stop it. But for alpha particles, do you know what you need to shield yourself from alpha particles? Just a piece of paper would work for alpha particles. Alpha particles are extremely reactive, so they'll react with paper as well. We'll talk more about these forms of radiation. Alpha particles are thought to be like quite a bit more damaging to biological tissue than X-rays and gamma rays. They have a quality factor. If you believe the quality factor and use it as is, it's like 10 times more damaging, potentially. Beta particles are electrons, but these electrons have an interesting origin. You know, these are electrons that come out of the nucleus. And so if you have a nucleus, how many electrons are inside a nucleus? 0. So how can we get electrons coming out of the nucleus? Do you know how electrons can come out of the nucleus? How electrons come out of the nucleus is if you take a proton and the proton decays into a neutron, it spits out an electron. And so, yeah, that's called, well, there are different names for this. That's called a nuclear reaction here, and we'll leave it at that. And so these are electrons, but once the electron gets spit out of the nucleus, you can't tell the difference. It behaves like a normal electron, even though its origin was from the nucleus. You don't need to know this. This is more Chem 1B stuff. So how does the radiation interact with fields? And so this is showing lead block to protect ourselves from radiation. And here's a radioactive material. And the radioactive material is decaying. It might be spitting out beta particles. Beta particles are going to be deflected to the positive because these are electrons negatively charged. Gamma rays are not deflected because they have no charge. And alpha particles are deflected to the negative. And so we need alpha particles for the next experiment. Do you guys recognize this experiment here? This is, the metal foil is usually gold. It's a very, very thin sheet of gold, and this is called the Rutherford gold foil experiment. And so there are two competing hypotheses. There was the plum pudding model and the gold foil, that is the nuclear atom model. And what was the evidence in support of the plum pudding model? Pretty much nothing, because the experiments supported the nuclear atom model. What was the evidence in support of the nuclear atom model? The evidence in support of the nuclear atom model was they took some radioactive radium. The radium shoots out alpha particles, so a chunk of the nucleus breaks off. These alpha particles hit the gold foil here and then hit a detector. Most of the alpha particles went straight through, and that's consistent with the nuclear atom model because the nuclear atom model states that the atom is mostly empty space. However, some of the alpha particles were slightly deflected. Well, that makes sense because if an alpha particle comes close to the nucleus is positively charged, alpha particle is positively charged, so they're going to repel each other, depending on how close they get. The closer they get, the more they repel. But some alpha particles bounce back, and these alpha particles must have collided directly with the nucleus. Because if you have an alpha particle positively charged and a nucleus positively charged, they're going to repel each other. And so you have strong electrical repulsions. And so this will bounce. However, it depends on how fast you accelerate the alpha particles. If the alpha particles are accelerated extremely fast so that the alpha particles stick to the nucleus, then we have a nuclear fusion reaction. And there we need a particle accelerator. This is not going to be fast enough. But they have particle accelerators where they can accelerate it faster and faster and faster and faster, and then boom, collide it and hopefully make a new atom. But chemists aren't doing that type of stuff. Chemists will just be looking at this. So this is evidence in support of the nuclear atom model. Whereas the plum pudding model, we would see a different set of observations. So these weren't observed. This was observed, however. And that would be the alpha particle scattering experiments. So that's a little bit of history here. And we didn't talk about the discovery of the proton. The protons were discovered by Rutherford. The same Rutherford as, what was the Rutherford? The gold foil experiment? Yeah, that's correct. The same Rutherford as the gold foil experiment. And the neutrons were discovered by Chadwick. And so if you're interested in those, you could look those up in the early 1900s. All right, so the mass of the electron was determined using dimensional analysis because from the cathode ray tube, what they got was the mass to charge ratio. Depending on what the mass to charge ratio was, it would deflect differently. The higher the mass, the less deflection. The lower the mass, the more deflection. And the charge. So if you take the mass to charge ratio times the charge, the charge cancels and leaves you with the mass. And so the mass that that was calculated in the early days is slightly off. The new mass of the electron is this one, 9.1094 times 10 to the minus 28 grams. The proton, the neutron weigh these. However, grams are terribly inconvenient. Even attograms are terribly inconvenient because attos are what, 10 to the minus 15? Is that right? P goes 10 to the minus 12, yeah. So 10 to the minus 15 is far away from these. And so we use the atomic mass unit. And the atomic mass unit is, what weighs exactly 1 U? Is there something that weighs exactly 1 U? I know there's something that weighs exactly 1 kilogram. It's that chunk of metal. Uh-huh. Proton, unfortunately, doesn't weigh exactly 1 U. Just a proton with nothing else weighs 1.0073 U. And a neutron weighs 1.0087 U. And so what weighs exactly 1 U? And the answer is nothing. There's nothing that weighs exactly 1 U. There is something that weighs exactly 12 U. What is it? Carbon-12 atom. And so, so there's nothing that weighs, and so the atomic mass unit is not defined by what weighs 1 U. What the atomic mass unit is defined by is what weighs exactly 12 U. But what you want to remember is this. These are easy numbers to remember. Qualitatively, what does a proton weigh? About a U, 1 U. And a neutron? About 1 U. So what we remember is just the proton weighs about 1 U and a neutron weighs about 1 U, and a neutron is slightly heavier or slightly lighter? Slightly heavier than a proton. That's all we remember for this. And that's good to, let's say, 2 sig figs. An electron is 1,850 times lighter. Here. And so about 2,000 times lighter. And so 1.0005. That's what a lot of people remember. But if we were doing more precise calculations, then we're going to use as many sig figs as we can. Does that make sense? Now, how do we relate U to grams? And the conversion factor is easy. Do you remember Avogadro's number? Yeah. I don't know. Am I using the wrong PowerPoint? Maybe. It's an easy conversion factor. You just take Avogadro's. There's an Avogadro's number worth of atomic mass units in 1 gram. So the conversion factor is easy. This is an easy conversion factor to derive, and we're going to learn how to derive it. We derive that conversion factor based on the definition of the U, carbon-12, and the definition of the mole, carbon-12, again. So we'll look at those 2 definitions later. So we know, pretty precisely how much a proton, neutron, and electron weighs. However, we can't just add up those masses. And we know the charge. The charge is on an electron was determined by the oil drop experiment by, who did the oil drop experiment? Millikan, yeah. And that's minus 1.6. But we can only have integer multiples of this. We can't have half electron or 1 1/2 electrons. So what they did was they kind of quote unquote quantized this. They just have integer multiples. So we might have 1 of these. If we had 2 electrons, we double that. So it would be minus 2. 3 electrons would be triple that, so minus 3. So this is just the integer multiple, and that's what we call the charge. If we're doing a physics calculation, then we'd use the actual charge here. So we know,
Is that conversion exact since Avogadro's number over 1 gram?
Is this conversion exact? It used to not be. This conversion at one time was not exact until.
Is that now how we define the gram?
Yeah. No, this is not how we define the gram. This is how we define Avogadro's number. Somebody said, what was it, 2 years ago? 1 or 2 years ago, somebody said, it just keeps going. It's like pi. It just keeps going, and then they said, it's too much, so they redefined it. And so what they said was, Avogadro's number is exactly this. So this is exact now. I don't know why they did that, But it's like saying, okay, pi is too many digits. I'm going to redefine pi and call it 3.14 to the disappointment of all those people who've memorized 50 digits of pi, That would be pretty bad, because if I memorize 50 digits of Avogadro's number, then I'd be pretty disappointed by that too. Yeah. Chemical elements here. You guys remember the elemental symbols here? The composition, atomic number, mass number. Okay, make sure you review that. You know, this tells us the composition of the isotope there. How many protons? Z. How many neutrons would be A minus Z? How many electrons would be the charge up here? You know, depending on what the charge is, we can figure out how many electrons there are. And so we need this here. We'll talk more about that later. And then we have the isotopic masses. So what I want to do here is this. We go until when? 420. I must have skipped some stuff. So I ended sooner. I was kind of rushing because I was thinking 4. But anyway, we'll do this. What we're going to do is, okay, you had a glass of water, and I told you that not all the water molecules weigh the same. There are some that are lighter, and there are some that are heavier. And what we want to do is we want to figure out all the water molecules that you had in your glass of water. And so we're going to build water. And water has a constant composition. It's always 2 hydrogens to 1 oxygen. It's not like we can't have 2.1. or 2.2. If matter were infinitely divisible, then sure, we should be able to have 2.1, 2.2, whatever. And so this is atomic theory. This is further evidence in support of atomic theory because it's going to come in simple whole number ratios like this. So if we're going to build water, we need to get 2 hydrogens and 3 oxygen. So what we do is we do some mass spectrometry experiments like this. If we knew the theory, we'd be able to predict this. And then we compile all that data in a table. The table is in our book. Let me find it. It's in Appendix D. We looked at Appendix A the other day. And so if we feed hydrogen into our mass spectrometer, these are the 3 data that we get. We get the number of isotopes. The number of isotopes is there's hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 2 and 3 have special names. Hydrogen 2 is called deuterium, hydrogen 3 is called tritium. And then we look at how many strike. Actually, we only see 2 strikes. This 3rd strike we don't see. You know why? Because tritium is radioactive, and so its percent natural abundance is nil. And so we can ignore this one. And so we're going to say that there are 2 naturally occurring isotopes of hydrogen. Most of the hydrogen is hydrogen 1. How do I know? Because 99.9885% of the strikes are hydrogen 1, and only 0.0115 strikes are hydrogen 2. The way I like to do this is I like to move the decimal all the way to the end. If I move this decimal all the way to the end, then I go 1 million. Out of 1 million hydrogen, the 999,885 are hydrogen 1, and 115 are hydrogen 2. So that gives us an idea of that. And so now I'm going to have a pot of hydrogen. I'm going to give you 1 million hydrogen atoms. Out of that 1 million hydrogen atoms, 999,885 will be H1 and 115 will be H2. So if you grab a hydrogen, you're most likely going to grab what? A hydrogen 1 or a hydrogen 2? Hydrogen 1, it's just so much more abundant. Oh. Okay, so we feed that. And then do you know how many isotopes of helium? 2, it looks like. Lithium 2, except beryllium. Beryllium only has 1. Boron has 2. If we knew the theory, we'd be able to predict this. Carbon has 3, except one of these, carbon-14, has 0 natural abundance, meaning it's radioactive. So carbon-14 is radioactive. We'll ignore that for now. And it's just carbon-12 and carbon-13. And these are the masses here. You know, we can get extremely precise masses. How many sig figs is that? 3, 6. This is only 8. This is only 8 sig figs, but we can get more than 8 sig figs now from mass spectrometers. Extremely precise, extremely sensitive they are. But how much does a carbon-12 weigh? It weighs 12 U to how many sig figs? 8? 8 sig figs? I don't know, this is kind of, they shouldn't have done it this way because it makes it look like it's only 8 sig figs. It's not only 8 sig figs because carbon-12 is the definition of the AMU, And so that's infinite sig figs. Doesn't look like infinite sig figs to me, but that's infinite sig figs. How do I know? Because I've memorized the definition of the U. And so this is infinite. Whereas carbon-13 is going to be 8 sig figs because that's relative to that. And so we use carbon-12 as a calibration standard for the AMU. And so this infinite exact. Uh-huh.
When we get, so when we're calibrating our machines, you know, we hypothetically using carbon-12, how do we make sure it's just carbon-12 if there's no carbon-13? Or do we pick up that somehow?
No, you don't worry about the carbon-13. It shows up. But what you're going to have is you're going to have a huge peak and a tiny peak. And the huge peak is because what I do is I'll just move it over. If I move the decimal over, that's 9,893. So if I had 10,000 carbon atoms, 9,893 will be carbon-12 and only 107. And so you're going to have a 9,800 peak and a 107 peak. So there's going to be, and so it's going to be very easy to tell which one's carbon-12. Sometimes it's not so easy to tell. But in this case, you don't have to separate it. And it's too hard to separate the isotopes. You know, it's not so easy, you know, because like some people wanted to separate the heavy water from the light water. How would you do that? To separate the heavy, let's say, you know, I'm on a diet. I don't want to drink the heavy water. I want just the light water molecules. And so I need to separate them. But is that something that's easy to do? No, but people did it. It's a very fascinating story how they separated heavy water from light water, you know. This is actually, and the reason they did it wasn't because they were on a diet. The reason they did it was because they wanted the heavy water for making a bomb, a nuclear bomb, basically. That's why they did it. And I think it was in Norway or something. Yeah, Norway. Oh, there's an interesting video. I'll show it to you on heavy water. But it's not so easy for us to do. But it's a surprisingly interesting way that they did it. But first of all, we want to see what the light water and the heavy water is. And so let's take a look at oxygen next. Oxygen's element number 8. How many isotopes are there for oxygen? 3. Could you have predicted it? Yeah, you could have predicted if you knew the theory. Do you know the theory? No. Maybe ask a physicist to tell you. They should know the theory. Well, anyway, 3 isotopes, and then you should ask them what the abundance of each isotope is and what the mass of each isotope is. If they could predict that, I'll be very impressed to this many sig figs. Maybe they can. That would be good. But anyway, when we look at it, there are 3. There's oxygen 16 with 8 protons. And how many neutrons? All these have 8 protons. Because oxygen's element number 8, Z's 8, they all have 8 protons. How many neutrons does oxygen 16 have? 8. How many neutrons does 17 have? And 18? 10, yeah. And then the electrons, if these are all neutral, they'll have 8 electrons. Okay, how much does each weigh? Well, oxygen 16 weighs a little less than 16. You know, that's kind of weird to think because a proton weighs how much? More, a little more than 1 U. A neutron weighs 1, an electron weighs about 0.05. So that's going to come out above 16, right? But the mass is below 16. Why is that? Why is the mass below 16? If I have 16 protons, that's 16 U. 16 neutrons, that's another 16 U. And then 16 electrons is going to be, I don't know, some amount of U. And so why is the mass lower than the individual masses? And it's because of the nuclear binding energy, the mass defect. And that's the case for all these. All of these have masses lower than the sum of their parts. But anyway, from the mass spectrometer, we can get all this information. And so what we're going to do is we're going to make water. And this is different than making, you know, cake or cookies or whatever, because, you know, they're going to be in chunks here. And so what are the parts? We have hydrogen. We have hydrogen 1 and deuterium, and we have the oxygen 16, 17, and 18. Hydrogen 1 is the most abundant. And let's take a look at the abundances for oxygen. When we look at the abundance for oxygen, the most abundant is oxygen 16, followed by what? 18, and then the least abundant will be. Now, why is that? That's our observation. And so what you need to do is you need to come up with a hypothesis. Can you come up with a hypothesis why 17 would be less abundant than 18? Well, somebody did come up with a hypothesis. You know what the hypothesis is called? It's called even-odd. Even number of protons and even number of neutrons is better than odd numbers. And so if you have an even-even combination, that's better than even-odd or an odd-odd combination. That's the hypothesis. But then why? Why is it even-odd? You know, and so we got to dig deeper and deeper. But we don't care about the hypothesis for us. We're just going to use the data. And that's it. And so let's take a look at the data here. So I built the first water molecule. I think I went to the wrong PowerPoint because I was supposed to build these. I guess I accidentally overwrote the file. So it's all right. So this is the grab bag of atoms. And water has constant composition, 2 hydrogens, 1 oxygen. So if I grab a hydrogen, most likely I'm going to grab a hydrogen. If I grab an oxygen, most likely I'm going to grab another hydrogen. So most of the water you drank today is H1O16H1, which weighs around 18 U. Hydrogen weighs about 1 U because it's got 1 proton, 1 electron. The electron doesn't weigh much. Oxygen has 8 protons, 8 neutrons. So that's 16, and then this is 1. So 16 plus 1 plus 1 is about 18. If we fed water into mass spectrometer, we can get 8 digits or more for the weight. But we're just approximating it. Okay, this is the most abundant. So most of the water you drank today is this. Okay, what's the next most abundant? What is the next most abundant? Would the next most abundant be H1, O16, H2, or would the next most abundant be H1, O18, H1? What do you think? H1, O18, H1? Okay. Well, we can easily calculate it. I'll show you how to calculate it. But for right now, the first part of this is tell me how many different water molecules are in here. Because if I want my diet, then I need to stick with just this and get rid of all the others, but I want to know what all the others are. Right? And so tell me what all the other heavier water molecules are in this. So the first part is how many different water molecules are in a glass of water. Okay, the next part of this is use some math to tell me what the percent abundances of each of those water molecules is. And the math is, I'm not going to give you an equation. You have to use dimensional analysis or conversion factor method to figure it out. I'll tell you how to do it. But why don't you work on this now and figure out how many different water molecules you can make with this grab bag of atoms here.